Welcome back, everyone, to the eCoreAcademy e-learning platform. Today, my name is AJay Raj, back with yet another geometry video for you all. Today's geometry lesson topic is all about directed line segments. But before we jump into today's lesson, please make sure to smash that subscribe button down below, hit that like button on this video to show your support, as well as turning on post notifications by hitting that little bell icon underneath the subscribe button. All three of those things are very greatly appreciated. As I was saying, directed line segments are a very simplistic concept in geometry, but there are various high-level concepts that can actually be related to directed line segments, such as partitioning and other exponential values that can be induced into this. Some of those high-level math concepts even include algebraic concepts that have to relate to functions, and it's going to be related to the coordinate plane. The coordinate plane has its whole plethora of difficulty, such as parabellums, parabolas, cubic functions, all sorts of those types of concepts. But today we're going to be looking at specifically directed line segments, which is relative to geometry. And I'm going to be showing you how to represent that on a coordinate plane, what it is, and how exactly we're going to look at it and its unique properties. So like I just said, just to reinstate, the whole theme and purpose of today's geometry lesson on directed line segments is to discover what are directed line segments and what are some of their unique properties when divided or partitioned. So we're going to be going through the process in which we identify what directed line segments are, what are some defining characteristics and points that they have, and we're going to see the actual process in which we partition different line segments given on a coordinate plane or a blank plane. Like I said before, blank planes are also very important. In previous videos, I've said that, but we're going to be looking at it on a blank plane overview, a coordinate plane overview, and then we're going to be looking at the unique properties created when they're actually partitioned. So let's jump right into it. Before we actually get to the directed line segment and the different formulas that you can utilize, let's look at the midpoint formula. Midpoint formula is very important when it comes to directed line segments and line segments in total, but it has to especially deal with directed line segments and partitioning. So let's look at the midpoint formula. I have mentioned this before, but I will be doing this as more of a formal introduction to the midpoint formula. So let's describe a midpoint before we actually get to the calculation part and the actual formula part where we actually use it to plug in values. So a midpoint is a point that divides a line segment into two congruent parts. I'll add an S there, so parts. So the midpoint, as the name itself offers information to you, it's basically a point, as the prefix point suggests. It's any point in space. However, midpoint suggests that it's going to be in the center of a line segment, and when a point is on the center of a line segment, you're actually splitting that line segment into two different congruent parts, two parts that are equivalent to each other, two halves of an entire whole of that line segment. And it has to be a line segment because line segments are the only types of lines, meaning excluding rays and your lines, they are the only types of form of lines that actually has a defined length. So you can actually calculate that with the distance, and therefore you would have a known midpoint. So a midpoint only refers to a line segment, and it's the center of that line segment given. And we're going to be representing that, of course, on the coordinate plane. And the horizontal and vertical lines as midpoints are found by dividing their measures by 2. So if you're given a horizontal or vertical line function on a if you're given a horizontal or vertical line on a coordinate plane, a horizontal line is a function, but a vertical line is not. But we'll get into that later. But you should already know that from previous algebra lessons. In Algebra 1, you were taught about the vertical line test, so on and so forth. So the horizontal and vertical lines, which are basically lines that go straight up and down, representing the y-axis, simulating that. And of course, your horizontal lines simulate the x-axis, going from left to right all the way across. So those are your vertical and horizontal lines here. And what I'm trying to say here is, if you're trying to calculate the midpoint of a vertical or horizontal line on a coordinate plane, you wouldn't need to do any specific calculations. All you would need to do is calculate the distance that these two line segments would have, or that your line segment would have if it's horizontal or vertical. And after doing so, you divide it by 2. And once you divide it by 2, you'll get the center point halfway in between your distances. Figure out what kind of coordinate that is, and then, of course, mark it as your midpoint. So what you're going to do is find distance. I'll label that number 1. So find distance. Divide by 2 in order to get halfway. So divide by 2, the halfway of that distance. And then you're going to add this value here, whatever value you get after dividing the distance by 2, you're going to add to one endpoint of your line segment. And finally, once you've added it to, once you've combined it with your endpoint there, you're going to get a new distance. You're going to count off from your coordinate, and then you're going to find the midpoint coordinate and give midpoint coordinate. And that'll be the midpoint of your line segment. So as you can already tell, I'll say give midpoint coordinate. So as you can already tell, the midpoint is obviously going to be some sort of form and some sort of involvement in actually partitioning our directed line segments, our whole topic of today. And that's probably the most basic, the most important, partitioning in a directed line segment, and of course a point on the directed line segment, because everything can be referred to based off of that under specific special case scenarios. So let's move on to fully unlocking the midpoint formula and calculations with the midpoint formula. And then let's jump into directed line segments, partitioning them, and plugging them into some problems with some of our new formulas. So let's look at the midpoint formula part 2. So let's calculate the midpoint. We're going to be putting this basically to work. I'm going to be showing you how to actually calculate the midpoint, where the midpoint formula will derive from, and then of course I'll show you what the midpoint formula is and how to actually plug it into given scenarios. So the midpoint is, of course, under the definition of geometry, can be referred to as the average of both x coordinates and y coordinates. For diagonal lines, use the midpoint formula. So all that information is very key. I'll break it down with you. So the midpoint is basically when you're taking you're combining your x values and your y values. If we're looking at a line will always have two line segment. If we're looking at a line segment, it will always have two endpoints, one starting point and one ending point. Once you have those two endpoints there, you're going to be utilizing those two endpoints given the coordinates on a coordinate plane. You're going to be utilizing them in order to calculate the midpoint of your line segment and all the partitions that go along with it. So in order to calculate the midpoint, you're going to be combining both of the x values as you would for slope, similarly in that manner, and you'd be combining both of those values, and you'd be finding the average, meaning the value that's between those x values. If you think about it, you're trying to average separate coordinates as you are trying to average the entire line itself. So you're finding the average of your x coordinates, which is adding them and dividing by 2. Similarly with your y coordinates, doing the same thing. And this applies for diagonal lines. You can use a midpoint formula for the diagonal lines, because diagonal lines on a coordinate plane, you would have to use the distance formula to calculate the distance, but you cannot count horizontal distance with the plain eyes. You cannot do that. You can only calculate horizontal and vertical distance just with your fingers. There are forms of it's similar to a dilation process. I will show you that in upcoming video on how you can do that on a coordinate plane, but this is a much easier process of doing so, and my partitioning equation are my partitioning formulas are much easier to follow as well. So as I said, it's going to be used for diagonal lines, and for vertical and horizontal lines you can just count it off. It's very easy to do so. However, the midpoint formula, I will say that in the next slide, it can be used for any line. This doesn't mean you have to use it for just for diagonal lines. You can use it for any lines in general. It's just much more convenient in order to utilize the standard counting process or your eyeballing method for your vertical and horizontal lines. So another thing to add, you cannot use the distance formula to calculate the location of an endpoint. Like I said, you might be thinking, well, if you have a diagonal line and it's not horizontal or vertical and you're trying to calculate some sort of distance, you can use the distance formula to calculate the distance of the line. Well, that doesn't necessarily help with calculating a midpoint, because a midpoint is a point on the line and it's not necessarily representative of a given distance. It's a point, and you aren't able to find the point in which the midpoint is located with the distance formula, but you will be able to find the relative length of the half of the line segment or the line segment given, but you won't be able to count it off and give the exact location. So midpoint formula is direction. I'll write this out here. So midpoint formula. Midpoint formula equals location oriented. So it's a location oriented, but it also implies distance. However, distance formula is length oriented. I'll say this length oriented because I don't want to reiterate distance, but it's length oriented and it does not apply location, unlike midpoint formula implying both variables. So length oriented. So that's important to know in this comparison. Length oriented. All right, let's move on. So the midpoint formula part 3, let's look at utilizing the formula. So let's identify what the formula is, and let's see if we can plug it into some sort of example. So the midpoint formula, I'm going to write this out here because it's much more difficult to write this in keyboard language, so I'll just write it out as you are, presumably when you're taking notes. So the midpoint formula is x1 plus x2 over 2, comma, y1 plus y2, and these are subscripts, over 2. So if you can see here, this is basically relating to our coordinates. And if you're given your original coordinates, and if I'm referring to my original coordinates as in x1, y1, my first pair of coordinates, and x1 and x2, y2. So if those are your endpoints of your line, then you just plug in these very values into your midpoint formula equation here. And you basically divide the sum of the coordinates as pairs. So you add both x coordinates together, divided by 2, and that would be your new x coordinate of the midpoint. And then take both of their y values, add them together, divide them by 2, and that will be your new y coordinate. And those two x and y coordinate, that x and y coordinate that you get from this formula will be the location of your midpoint of the line segment. And you're just dividing them by 2 to get the average of them, as it works for any line segment. Like I said before, you don't necessarily only need to use this for diagonal lines. You can also apply this to horizontal and vertical lines. However, it's just much more inefficient in doing so. So I'll give you a little example here. I'll draw this line segment out here. Draw it up here. And let's say that this is on a slight incline here. Let's say this is on a slight incline and it's not a horizontal line. It's on a bit of an incline here. So we cannot simply count it off and calculate the distance by counting, like I said. So let's say that this point here is going to be 3, 1, and this is going to be 4, 2. What is the midpoint of this diagonal line? So I'll write this here, diagonal. And the answer to that would be utilizing this formula, of course. So let's say, for example, that 3, 1, this is our x1. I'll write this over here. So let's say that 3, 1, our first coordinate here, one of our endpoints of our line segment. Let's say that this is x1, y1, and that this coordinate here is our x2, y2. We're going to plug these values into our midpoint formula. So let's plug them in. So we'll take x1 here, which is our 3 value here. So that's 3. And then we're going to take our x2 value here, which is 4. Add that and divide that by 2. And then put a comma separating that because it's a coordinate pair, making a new coordinate pair. We'll take our y1 value, put that on top, add that to our y2 value, which is equivalent to 2. So that's 1 plus 2. We'll divide the sum of that by 2, and then we'll simplify that. So that equals 3 plus 4 is 7. 7 divided by 2 is 3.5. 1 plus 2 is 3, and 3 divided by 2 is 1.5. So the midpoint here is equivalent to 3.5 comma 1.5. So that's halfway between both endpoints, and it's the midpoint of this line segment. Very simple concept, but we're going to take it a little bit further. And I have already introduced this concept to you during one of my problems in a previous video of mine, but I'm just reinstating that, putting into geometric terms, and we're actually going to plug this into higher level concepts with directed line partitioning. So, like I said, we're going to move on to directed line segments, the main focus of today's lesson. So this is part 1 of directed line segments, and we're going to look at just exactly what are directed line segments. So directed line segment. A directed line segment is a segment between 2 points, A and B, just as any segment is between 2 different points, and in this case, we're labeling them A and B. And this line segment will have a specified direction, either moving from A to B or from B to A, and with a standard distance between 2 points. So I'll break that down after this. So you need the ratio and direction to partition a line segment. So we're going to be looking at how we can partition directed line segments. So like I said here, you need the ratio in which you want to split the line segment into, and the direction in which the line segment partitioning is occurring. So an example of that would be if you had a line segment here with points A and B, and you were trying to say that you're moving from this point, leftmost point, to the rightmost point. What you would say is line segment. This would be a line segment A, B. That's how you convey it. You don't necessarily need the dots on the end, but that's just for extra identification, super identification. And then if you had another line here with B, A, and you wanted to say that this line is moving from B to A, this directed line segment is moving from B to A, well, then that would just be BA, B coming before the A. And you don't need to put the dots on here because we know we're talking about line segments, but you can always do that to be sure, make sure you're clarifying what exactly you're looking at, what you're referring to. And another important point is obviously your ratio. So when you're splitting a line segment up, you want to have a ratio. So your ratio is telling you what side is going to be compared to what side. So if you're looking at a midpoint formula, if you're looking at the midpoint of a directed line segment, what you're going to be saying is I want a 1-to-1 ratio, meaning both halves of that line segment will be equivalent. Both parts of the line segment that you're splitting, both partitions will be equivalent. However, if you're saying, say for example, 2 to 3, a 2 to 3 ratio, and that's represented by a colon. So an example of that, this is right here. If we put a point here, that this could be represented as 1-to-1, and if that's a midpoint of this directed line segment. However, if we want to say this is a 2 to 3, 3 to 2 line segment partition, we can say 3 to 2, and that's the ratio of the first part of the partition, the first partition to the second partition. And the way that works is it's only going to be 2 partitions allowed in this concept here, but of course you can use it later on. You only need to know how to partition it twice in order to give an overall estimate of what you're going to be doing later, because we're just simplifying this ratio here. So that's what your partitioning ratio gives you. It starts from your first point, whatever you clarify. Say, for example, AB here, we have line AB. It's going to be starting from point A and moving one partition here and one partition there. But if you look at line segment BA, we're going to be starting from B and moving 3 over and then 2 over. And if you can tell here, if you have 1-in-1 ratio, if you have a 1-to-1 ratio, you're going to be splitting the line into 2 different parts because you have a 1 compared to a 1 ratio. And also, likewise, if you have a 3 to 2 ratio, that means you must be splitting the line segment into 5 equal segments, in which 3 of those segments are going to be from B to whatever point you've marked off, and the other part's going to be A to whatever point you've marked off. And of course, directed line segments have a standard distance, so they're all going to be relative. So say, for example, this is this value here, we don't know yet. It's going to be worth 3x. That means that this side must also be worth 2x because it's all of standard relationships. And if this is worth 1 in line segment AB, if it's worth x, then this side must also be worth x as well. So I'll draw that ratio colon right there. All right, let's move on. Directed line segments part 2. let's look at partition calculation with directed line segments. This can actually get a bit confusing, but I'm here to break this down for you and shine some light on this concept, because it's actually quite convenient. More than it is complex, it's much more convenient. And of course, I'll be helping you right here, right now, with the complexity. So you can calculate an even partition if the total number of partitions needed is a power of 2. And what I mean by that is, oops, sorry about that. So if you have a partition, the number of partitions, like I said, if you have a ratio like 2 to 3, and you know that you need a certain amount of partitions, like 2 to 3, you would need 5 partitions with 2 segments given to one side, 1 partition, and 3 segments given to the other. Likewise, you would need to know how many partitions you need in total. And the way to do that is before I get to that, all you need to know is the total number of partitions, because in a directed line segment, if you know the ratio that's given, say for example 5 to 6, and you know that you need 11 segments because it's a 5 to 6 ratio, you're going to add them together to get 11 total partitions that you need. And once you've done that, the problem itself has been solved. You're going to add those points on your coordinate plane on the line segment represented on a coordinate plane, 11 even partitions on that directed line segment. And after you've done that, you're just going to count up 5 from the starting line segment, the line segment that's going to be starting the direction going the other opposite way to the other point. So you're going to be starting with a starting point and then counting up 5, marking that spot off, and then you're going to leave the remaining partitions there, because that'll remain 6 of the entire 11, and that'll give you a 5 to 6 partition ratio. So all you need to do is calculate the number of partitions that you need. If you have a partition that is a power of 2, that means that you can easily calculate that using the midpoint formula. However, if you don't, there's another sectional formula that you have to apply on top of the midpoint formula. So say, for example, we have this line segment here, and I'm going to put the coordinates for, I'll make this a bit more inclined. Drastic enough. I'll make this a bit more inclined. Keep in mind, this is all mainly for horizontal lines. Mainly for diagonal lines. So let's say that this is 4, 1, and that this point over here is 6, 3. What we're trying to do here is, say for example, I want a partition in the form of 3 to 4. 3 to 1. I apologize. 3 to 1. Now, if we look here at this example, 3 to 1 partition, that means that we have to have a total of 4 partitions in our line segment here. So we need 4 partitions. 3 of them from left to right will have to be classified as 3 in this ratio, and then 1 is the remaining side partition. So 4 equivalent partitions are needed. 4 partitions. So in order to do so, what you can do is you're going to calculate the midpoint of these 2 points given. So we can do that right here. And since it's a power of 2, 4 is a power of 2, we can merely just repeat this process for the needed given amounts. So once we calculate the midpoint of this given line segment, 4, 1, and 6, 3, we'll find our midpoint. And then, of course, we're going to calculate our midpoints from each side of this line segment in order to get 4 equivalent partitions, and we can deliberately direct our 3 to 1 ratio with the given circumstance. So let's calculate the midpoint of the 4, 1, and 6, 3. So 4. So this is going to be x1, x2, and y1 and y2. Let's work from left to right. So we're going to add 4 and 6, divided by 2, and then add 1 and 3, divide that by 2. And we get 10 divided by 2 is 5, and 4 divided by 2 is 2. So that's 5, 2. So we're assuming that 5, 2 is right here. And then after you found out that it's 5, 2, next what you're going to do is you're going to take 5, 2, calculate the distance from 4, 1, as well as the distance from 6, 3. So let's do that over here. Let's calculate the distance between the midpoint of 5, 2 and 4, 1. Let's add 4 plus 5 divided by 2, 1 plus 2 divided by 2. And that equals 4.5 comma, and then 1.2 plus 3, 1.5, 4.5, comma, 1.5. So that's our midpoint here, 4.5, comma, 1.5. And then we'll calculate our final midpoint here between 6, comma, 3 and 5, comma, 2. So let's do that over here. So 5, let's say that x1 and y1 is 5, comma, 2, and x2 and y2 is 6, comma, 3. So we're going to add 5 and 6, divide that by 2. And we're going to add 2 and 3 and divide that by 2 as well. Add 2 and 3 divided by 2. And that gives us 11 divided by 2, which is 5.5, comma, 5 divided by 2 is 2.5. So we'll write that down here, 5.5, comma, 2.5. So we can mark that off here as 5.5, comma, 2.5. Once we've done that, we can immediately put our partition right here. So I'm going to clear this out here so that it doesn't get in the way. I'll draw that out on the bottom again. 5.5, comma, 2. Once we've done that, we can deliberately draw our partition right here to say that this splits the line into a 3, comma, 1 partition, with this side being the 3, this side being 3 over 4, 3/4 of the line segment's length, and this part being 1/4 of the line segment. With all those points given, that is our final answer. Finally, let's move on to directed line segments part 3, and let's look at the section formula. This is for specifically for any lines that basically do not fall under the category of what I had previously given and previously stated, with the total number of partitions being a power of 2. This is for everything else. This is most common because you're most likely not going to be dividing a line smoothly with a power of 2 as your partitions get larger and larger. So the section formula states that if you're given a directed line segment and you're trying to split that line segment into a ratio of m to n, meaning one value to another value, the ratio the equation in order I apologize. The equation in which you're going to plug those ratio values into would be this section formula given here. So it's the mx2 plus nx1 over m plus n, comma, my2 plus ny1 over m plus n. So this formula is for a number of partitions that is not a power of 2. Like I said before, it's not as smooth, but it is very efficient with this equation, given much more difficult if you didn't have the equation, nearly impossible actually. But if you look at this equation, it's actually very simple, and that's if you're given same type of coordinates, like I said before, x1 and y1. If you're given the coordinates in x1, y1, and x2, y2 form, these are the endpoints of your directed line segment. So make this a bit more deliberate here. x1, y1, and then x2 and y2. And then basically what you're doing is you're taking each one of your ratio values and you're multiplying it to each coordinate here. So m is being multiplied to x here, as n is being multiplied to the other x coordinate, and then you're dividing it by the sum of the two ratio values here. So it's very simple here, very simple equation here. You're multiplying your ratios with both coordinates, each one being multiplied to a different coordinate here. M is going to be multiplied to both the x2 and y2 coordinates, and n will be multiplied to both the x1 and y1 coordinates. And you're going to keep it consistent. M is going to be the first coordinate, the first number that's going to appear in your ratio value, and n will of course be the second one. So if I'm going to draw another horizontal line segment here, and let's say that we have the coordinates 3, 1, and 5, 4. Now, in this directed line segment, I want to actually partition this into a fairly simple one. Let's do a simple one here with this equation because it's actually quite large. Let's do a 1 to 3 split. 1 to 3. I apologize, not 1 to 3. 1 to 2. That's what I've written down. I apologize. We have a 1-to-2 ratio that we're trying to split this into. Going from left to right in this case. So I'll say A, B here, and we're going to be going from A to B. So we have to find that one partitioning point, but we have to split this whole entire line into 3 different segments in order to actually do so. So what we're going to do here is we don't need to do the partitioning method like I said before. Splitting it up into different forms, it's not going to work with a value that's not a power of 4. But in this equation, it gives you the exact point in which you're going to have the partition. So it's actually, in essence, a lot more convenient than the power of 2 equation there. So let's try this out. Let's plug these values into the equation. So we're going to take our mx2 and x1. So let's make this our x1 y1 pair, and we're going to make this our x2 y2 pair as well. So let's plug that into our equation. We have our m value here and our n value here. We'll multiply that into the section formula, and that's going to be 1 times our x2 value, which is 5. So 1 times 5 plus n, which is 2, times our our x1 value, which is 3. And then we're going to divide that by m plus n, which is 1 plus 2. Separate that with a comma. And then we're going to take our m value again, multiply that with our y2 value. So that's 1 times 4. And then add that to n times our y1 value, which is 1. So it's going to be 1. It's going to be 2 times 1. Apologize. 2 times 1. And then, of course, divide that by the sum of m plus n, which is 1 plus 2. And then we're going to solve that down here. So 1 times 5 is 5. 2 times 3 is 6. 5 plus 6 is 11. And then so you have 11 up here. So the sum of these two is 11. So 1 times 5 is 5. 5 plus 6 is 11 here. So that's our sum here. And then 1 plus 2 is equivalent to 3. So it's going to be 11 over 3 as our x coordinate here. So 11 over 3, comma. And then we're going to multiply this side together. So 1 times 4 is 4, and 2 times 1 is 2. So 4 plus 2 is 6. So they add to 6. And then 1 plus 2 is 3. So we're going to keep this at 3. 6 divided by 3 is 2. So our y value is going to be 2. So the partitioning segment here is going to be 11 over 3, comma 2. And it's going to be in the form of 1. It's going to be in the form of a 1-to-3 ratio. So that's 11 over 3, comma 2. And if we split that here, this segment here will be our 1 third. Sorry, a 1-to-2 ratio. I apologize. So that'll be 1/3, and this here will be our 2/3. This side being 1/2 of this side. All right, everyone. Thank you for sticking through and staying with me through this entire video. I know it was a bit more complex of a video, but in the end, I hope you guys got the lesson, got it ingrained in your heads, and I hope you all enjoyed. That's most important. Hopefully, you guys are all enjoying this geometry course as much as I am making these videos. Once again, everyone, this has been the eCoreAcademy e-learning platform today. Please make sure to like and subscribe down below and turn on post notifications by hitting that bell icon. Feel free to comment down below. Of course, we love all of your constructive feedback. Also, make sure to visit our website at www.ecoreacademy.org. There we have full access to what we actually offer as an eCoreAcademy e-learning platform, as an e-learning educational platform in general as well. We have full unlocked access organized into course studies, all of our courses and subjects. There we have full unlocked access to integrated worksheets, note sheets, and quizzes that go along with each and every single one of our videos that are organized into different lessons with, of course, progress checks, progress bar that basically tracks your progress throughout your entire course. All you need to do is make an account for free at our website, and you have full unlocked access to everything that we offer. Also, feel free to email us at eCoreAcademy@gmail.com if you have any questions or if you just want to reach out. And finally, please visit all of our social in the description box below. We have the full links down there at Facebook, Twitter, and Instagram. See what kind of interesting content we have there, and use our Medium to actually share all of our videos as well. Yeah, all of those things are very greatly appreciated. Once again, everyone, I hope you all enjoyed. This has been AJ Raj, and I will see you guys in the next one. Peace.